My name is Ravenska Wagi, and my talk today is on the expansion of mesenchymal stromal cells and production of extracellular vesicles in an animal component-free culture system. I will begin by focusing on mesenchymal ACF+ as a single medium for both MSC expansion and their extracellular vesicle production, followed by discussing scale-up of MSCs in bioreactors. And finally, I will share our customers' data on their application of mesenchymal ACF+ for MSC-derived EV production at scale. So, as depicted in the graph here, MSCs have been broadly evaluated for their therapeutic applications. This is partly due to their paracrine signaling, which is mediated through the release of extracellular vesicles. As we know, EVs are nano-sized membrane-bound vesicles containing cargo from their cell of origin, and studies have reported that MSC-derived EVs, or MSC-EVs, have similar immunomodulatory and tissue repair capabilities to their parent cells, and so EVs themselves can act as non-cell-based therapeutic agents for similar disease indications as MSCs. However, some challenges of MSC cultures and their EV production in the field include the use of serum in culture medium, which can increase contamination risk, and the unknown variables inherent to animal or human-derived components can introduce variability and pose safety concerns in translational research, while the increased batch-to-batch variability compromises reproducibility and product consistency. It is known that animal-derived media supplements are rich in exogenous EVs, which is not ideal for EV production. Yet, the EV removal process may impact the quality of both cultured cells and their associated EVs. Thus, producing both MSC and EVs at clinical scale while maintaining quality and consistency remains a challenge. And to address this challenge, STEMCELL technology has developed mesenchymal ACF+ medium for MSC expansion and their EV production. This ACF formulation provides batch-to-batch consistency, contributing to the reproducible and controlled MSC and EV quality, and most crucially serves as single formulation, supporting both MSC expansion and EV production from diverse tissue sources. And conventional MSC expansion media such as FBS or human platelet lysate or AB serum containing medium contain their own EVs, which is a limitation for EV production itself. So in addition to being an ACF formulation, mesenchymal ACF+ also enables robust MSC expansion. As shown in the graphs here, mesenchymal ACF+ medium performs similar to human platelet lysate containing medium and clearly outperformed FBS containing medium and EV depleted FBS media in supporting MSC expansion. This medium also supports robust MSC expansion from multiple sources, including bone marrow, adipose tissue, umbilical cord, and human pluripotent stem cells. We then investigated whether mesenchymal ACF+ is EV-free. Our NTA data indicated that mesenchymal ACF+ medium contained at least 90% fewer nanoparticles than serum and human platelets containing media. And more importantly, the three EV markers, CD9, CD63, and CD81, are undetectable by Western blot in 6 lots of fresh mesenchymal ACF+ medium, while present in the mesenchymal ACF+ MSC conditioned medium. Given that this ACF medium enables MSC expansion and is EV-free, we further characterize the EVs generated by MSCs in the 2D culture system. So first, we expanded bone marrow MSC in mesenchymal ACF+ medium. Their conditioned media was then collected for EV isolation either by ultracentrifugation or size exclusion chromatography. Then the collected EV size distribution and particle concentration were evaluated by NTA and their EV-specific cargoes analyzed by RT-qPCR. So the NTA and qPCR data revealed that MSC EVs generated in mesenchymal ACF+ have the typical EV size, and the microRNA cargo characteristics of MSC-derived EVs. We then ask, are these EVs functional? So we utilize the UVEC2 formation assay to evaluate the biological function of isolated MSC EVs in vitro. As you can see here, the EV-treated cells are able to increase angiogenesis as depicted by the increased network branch points compared to control, indicating that MSC EVs here are biologically functional in vitro. Thus, so far, we have shown that mesenchymal ACF Plus enables robust MSC expansion and production of functional EVs in monolayer cultures. However, for potential clinical translation, scale-up protocols are required. So in the next few slides, I will discuss the optimization of scaling up MSCs in bioreactors with mesenchymal ACF Plus. To reach clinically relevant dose, optimized scale-up protocols are essential for efficient MSC production and for better control of process parameters in culture. So we have optimized an ACF suspension culture protocol in both spinner flask and PBS-MINI vertical wheel bioreactor by evaluating critical parameters. This includes microcarrier selection, MSC seeding density, agitation protocol, medium composition, and the dissociation step while maintaining an ACF workflow. This protocol optimization study was done in collaboration with scientists from Corning. Our optimized ACF suspension protocol is initiated with a seeding phase for about 20 hours, followed by an expansion phase of 3 to 4 days prior to harvesting. Important to note that the use of Corning dissolvable microcarriers circumvents the harsh cell dissociation step from the microcarrier and the subsequent need to filter out the microcarrier, yielding high viable MSCs. So this protocol resulted in robust MSC expansion in both spinner flask and PBS-MINI vertical wheel comparable to the monolayer culture. So the doubling time is around 1.2 days, which is quite efficient, while maintaining the MSC marker expressions such as CD90, 105, and CD73, and the trilineage differentiation potential into osteogenic, adipogenic, and chondrogenic lineages. With regards to yield, this table shows the cumulative MSC yield in 100 ml spinner flask. With an initial seeding of 750,000 cells at P1, after about 20 days in culture, the MSC yield at harvest is 100 billion cells, indicating efficient cell expansion with mesenchymal ACF Plus in suspension culture. So in the last section, I will present data from our customer, Dr. Marta Costa's publication, focusing on enhanced bioprocess control in manufacturing MSC-derived EVs in stirred tank bioreactors. So this group has developed a scalable production of human adipose tissue MSCs and their derived EVs in a BioBlue bioreactor platform with glucose control. Their proliferation data demonstrated that first, expansions of adipose tissue MSC was supported by culture in mesenchymal ACF plus medium and Symptomex2 microcarriers. And these MSCs retain their MSC surface markers and their trilineage differentiation ability in both static and suspension cultures. The use of Raman spectroscopy allowed continuous glucose tracking in suspension cultures. So conditions of low and high glucose were investigated as metabolic preconditioning strategies. So when suspension cells were cultured in mesenchymal ACF plus alone, without glucose supplementation for 7 days, the glucose concentration dropped below 1 millimolar. This is indicated in the black line, whereas the high glucose concentration in blue was maintained by supplementing glucose from day 2 onwards. Here, the EV yield data demonstrated that cell culture in suspension maximizes the ability of MSC to secrete EVs in comparison to culture in static system. And interestingly, cultures in mesenchymal ACF plus medium alone without glucose supplementation further improves the EV yield. They then further characterized the EVs from their system. The TEM data nicely revealed their manufactured EVs are intact, with typical cup-shaped morphology, possessing the characteristic EV markers of CD9, CD63, and CD81, and the EVs are uptaken by HUVEC. Furthermore, the EVs are functional, as demonstrated by promoting an increase in both cell migration for wound healing and in angiogenic potential compared to static culture in vitro. Thus, in summary, we have shown that mesenchymal ACF plus medium is a single ACF formulation supporting efficient MSC expansion in both 2D and 3D culture systems and generate functional MSC EVs in vitro. So in closing, stem cell technology has many product offerings to support your MSC EV workflows. Thank you for your attention.